A key part of this is that, like any statistical model, in order to be validly applied, there are a certain number of assumptions that have to be met. In our case, typically referred to as the Gauss-Markov assumptions, and these say that under these assumptions, which we'll visit in just a moment, then the least squares estimator is known as the best linear unbiased estimator, or BLUE. Now, here's what I mean by these three terms. Best means it is the estimator that has the least variance, or in other words, it's the most precise estimator of the parameter. Linear just means that the effects add up linearly. And finally, and crucially, unbiased, meaning this particular estimator on average yields the correct parameter. Okay, so if you put these all together, then you have the real definition of a BLUE estimator, which is the most efficient estimator in the class of unbiased estimators of the parameter. In other words, there might be more efficient estimators than the BLUE, so estimators that are even more precise than the BLUE. But if such an estimator exists, it has to be biased. In the class of unbiased estimators, this one here is the most efficient. Just to give you an example of bias and efficiency, let me show you this. So this is just a nice visual depiction of bias and variance. So here we're imagining that the bullseye is the parameter, the real parameter. And these little dots are experiments and estimations. So of course, the best case scenario would be something like this, a case where the estimator has low bias, meaning on average, the estimator hits the bullseye, and also low variance, right? All our estimations are pretty tightly packed, close and around our parameter. Now you might compare that to a situation of low bias but high variance. So this is a case where, on average, right, if you were to average all of our estimations, we would be right on the bullseye. However, there's a lot of variance. So our estimations are not tightly packed around the parameter, but they're kind of scattered around it, but still in an unbiased fashion. And you can compare that to the situation of high bias and low variance. Now, again, our estimations are tightly packed, so they have very low variance, but they are all systematically biased. And the bias is really the difference between our parameter and the barycenter of and the expected value of our estimator. And finally, of course, the worst of both worlds, something like a high bias, high variance. So not only the estimator is biased, clearly the barycenter of it is somewhere out here, but also there's a lot of variance around the biased, about the biased estimation. So, what are the Gauss-Markov assumptions? Well, written right here, the error has to be independent and identically distributed, IID, as a normal with mean 0 and variance sigma squared identity matrix, I. Now, I'll break this down in its three components, which are first that the expected value of the error has to have mean 0. The second is that the variance of the error has to be the same at every time point. So all the errors at each time point have to be the same, or in other words, you might know this as homoscedasticity. A typical example of violation of homoscedasticity, in other words, heteroscedasticity, is the fact that response times typically tend to be heteroscedastic. the longer the response time, the greater the variance. Right? So that would be a violation of the homoscedasticity. And this usually is not a big deal in fMRI. As we're going to discuss later, usually the big problem in fMRI is the next part of the assumption. And just to show you what I mean by homoscedasticity, if you take the variance-covariance matrix, then the main diagonal has to all be sigma squared. These all have to be equal and all have to be sigma squared. So that would imply homoscedasticity. And finally, the third, and as I was anticipating, the biggest problem of them all in the context of fMRI is the assumption that errors are independent of each other. In other words, there's no relationship between the error at time point 1 and the error at time point 2, or the error at time point 3, time point 4, time point 5, et cetera, et cetera. So again, which is also known as autocorrelations. So the assumption is that there's no autocorrelation. And we will discuss whether this is the case or not later. And in terms of our variance-covariance matrix, it simply means that all the off-diagonal elements are all the same and are all equal to 0, which is why we typically describe the variance as sigma squared I, or identity matrix. Now, finally, for the purposes of this class, inference will just be our boring t-test, nothing else, which you can see expressed here in terms of beta and variance of beta.